SAFE Software is pleased to present the 2009 FME International User Conference. This session is presented by Danielle Pilon, a Senior Project Officer for Natural Resources Canada. Danielle has more than 20 years of experience in geomatics and has worked on several projects involving data distribution and metadata management. He was also part of the team that began digitizing Canadian topographical maps in order to create the National Topographic Database.
Welcome everybody. Thank you to be here for my presentation on the generalization of 250,000 at Natural Resources Canada. My presentation will cover three main topics. First, give some context on the production of the 250K at topographical mapping at NRCan. Talk about a little bit of theory on generalization. I know it's not always fun to talk about theory, but we don't have the choice if we want to achieve good generalization, we have to talk about some theory. And also I will talk about the prototype we did using FME 2010. So topographical mapping in Canada, 10 million square kilometers to map. Well, that's our challenge. France is about 600,000, UK 300,000. So the land is our big challenge. Another challenge in Canada that mapping is a shared responsibility between the province and the federal government. But it also brings opportunities like the GeoBase initiative where we pool resources together to make some mapping. 150,000 is our base mapping that cover almost all the country because we still have 800 tiles, Baffin Island, Ellesmere Island in the north where there is no base mapping. Provinces are doing some mapping at 10K, 20K, but sometimes this doesn't cover all the province. So the real base mapping is 50,000 in Canada. 13,000 map sheet at 50K, a little bit less than 1,000 at 250K. Our product, our 250K product that we call the NTDB is old. The mean file average, the year is about 30 years old. But it is still widely used. 250K is a reconnaissance scale used early in early phase in the project. In the north, for people in the north, often it is their base mapping because of the land so vast. For them, a good, reliable, precise, up-to-date 250K would do the job. And in Canada, data are free, so we're able to monitor the data, and we know that there is still a lot of download for the 250K. Also, the 250K product is not aligned with our newer CanVec product, 50K. When I say it's not aligned, I mean both products don't share the same semantic, they don't share the same attribute name, attribute definition, spatial relationship. So there was a kind of emergency to act and create a new CanVec 250K product. The goal of this project is to derive automatically 250K topographical map from our database at 50,000. And it's a good time to do this because we have just recently finished all the vectorization of all our paper maps. We have improved the precision of all our digital files using Landsat imagery coming from the GeoBase project. We have completed the update of all the northern file using Landsat imagery. And also I was talking about those 800 files. Well, we are terminating. We've got a project to finish that mapping. So generalization model used. I'll talk about our generalization model used in the prototype. So some fact. Automatic generalization is a very complex process. Why? Because it tries to simulate the behavior of a human cartographer who is doing all the job by hand. And the market presently offers few complete solutions. In ESRI, you will find a couple of good generalization algorithms, but that's it. Intergraph is rewriting their Dynagen product. There's a company in the UK, One Spatial Formula Laser Scan, who's offering a solution, but more aimed at larger scale and more for building generalization, urban areas. So we decided to start a collaboration with Dr. Nouri Sabo from Laval University in Quebec City, who is a specialist in generalization. And we decided to implement a subset of his model. Whatever the system you're using, these are the principles that you have to stick in order to achieve automatic generalization. You need tools to monitor the properties of your object. You need tools to monitor the properties of your object when the object states change. When you aggregate two objects, well, now you have to recalculate almost on the fly a new area. You must also know that some elements have disappeared, no more relationship between two elements. You need a simple and efficient way to decompose the task of the cartographer, because the cartographer, when he is generalizing a lake, he is doing maybe 10 tasks in one step. You need a way to decompose that information. This is the model that we have implemented. So we start with, of course, initial data, hopefully generalized data at the end. What is important are, here on the left, the different levels. There's a measure level, a constraint level, a behavior level, and an operator level. You'll see that slide many times, and we'll go through it in detail. So measure levels. The measures are used to calculate the different characteristics of our map objects. It can be one object, a group of objects. Example, to calculate the distance between two contour lines. Very important, measures are used before generalizing to know how to generalize, but it is also done after generalizing to assess if we achieve good generalization. Measure can involve simple formula, the length of a line, or can be more complex tools or transformer in FME to calculate like a triangulation to compute a proximity. Also, the measure knows nothing about generalization. Second step, the constraints. From your target map specification, we all have target map specification, we can derive constraints. The constraints are the rules that are applied to data in order to comply with the requirement of your target map specification. Constraint can be applied to one feature, keep a minimum length, or it can apply to a relationship between several features, like if you want to keep a connectivity within a network. Constraints are used to verify. Constraint will use your measure, and this is how you make the link with the measure. Use the measure to verify the degree of satisfaction of your constraint. And of course, to achieve good generalization, a feature might need many constraints. Behavior level. This is the most complex level. This is why we have broken it into two levels. Into a macro behavior and a micro behavior. At the macro behavior, we call it generalization case. It is a formalization of the cartographer's knowledge, generalization rules. And it's a communication rule between the cartographer, who knows how to generalize a map, and the analyst, who will go after that behind his workbench to do the generalization. Generalization also allows to hide the complexity of how do we generalize. And we don't tell in the generalization case which algorithm or parameter to use. This is a real case of generalization case. Like you see, it's in natural English, very easy to read. You can have a good communication with your cartographer. Like on this example, for all vegetation, which breaks the constraint dimension area, which means for all the small vegetation. If the vegetation breaks the constraint position proximity, is there nearby another vegetation? Well, aggregate those two areas. Otherwise, eliminate the area. We see that the generalization case, we talk in terms of constraints and also generalization operator that we'll see in the next slides. Generalization behavior. This is the motor. This is the engine which will control the generalization case. It provides the bridge between the constraint and the operator. It is the mechanism, and it's sometimes very complex to choose which algorithm to use, which parameters you will also use. Last level, generalization operator. Generalization operators are typical and recurrent transformation that you have to do in order to do generalization. This is the way you will decompose the task of the cartographer. When a cartographer is, like I was saying, generalizing a lake, he is doing probably 3 or 4 tasks at the same time. These operators are abstract transformation, and you will find them well documented in the literature. But of course, they are implemented using a variety of algorithms, and this is those algorithms that you will find implemented in FME. Example of generalization operator: selection, simplification, smoothing, aggregation, simplification, enlargement, collapse. There are about a dozen of those words. And for each operator, you will have an implementation using different kind of algorithm depending on the situation. For line simplification, you can have Douglas-Puker, Lang, Wang. These are concrete algorithms. So I think you have enough of theory. So let's go in practice and see some results using FME 2010. We choose a region for the prototype that was not too difficult, not too easy, with moderate topography, and we targeted five entities: contours, water body, watercourse, vegetation, and wetland. And also we did a contract, thank you, the people of Safe Software, with to enhance FME with a new algorithms. If we go back to our models, the new tools were targeting the measure levels and also the operator level. So line simplification, we'll go through different kind of operator now, like line simplification, and I'm sure we all have in mind Douglas-Puker for doing line simplification. Does it simulate well enough the behavior of the cartographer? Well, I developed my own little Mythbuster test, especially that I'm on television. So let's do it. In red, we've got the original contours. In black, contours with a Douglas-Puker at 10 meters. So little animation at 20 meters, 30, 40, 50 meters. Yee, are we happy? Douglas-Puker is doing his job, which is trying to keep all the details of a line. But this looks more as a Pokemon drawing than real contour line generalization. So I think the myth is bust. Douglas-Puker is not good for generalizing at least natural feature. I haven't done tests with man-made feature. Well, this is why we ask FME to implement the Wang algorithm. The idea behind this algorithm is not to keep all the details. It's the opposite, to remove some details. Like this, on this example, I pass it with 150 meter. 150 meter for 250K maps represent about 2/3 of a millimeter on the map. So we achieve good result with natural features, vegetation, water body, wetland, and we can adjust the tolerance. Aggregation, we ask FME to implement 3 types of aggregation: by addition, convection, and by buffer. The best results were really achieved by aggregation by addition. The idea is to build triangle between nearby objects, to merge those triangles according to some criteria, use that merge area to aggregate the feature. This results are very good. This one was done as a custom transformer, and having Dale in the room, it would be nice to have that one role as a core transformer. So this is a real example with contour heights. We can see that we were very happy of the result, and we achieve also good result with other natural features: vegetation, wetland, hydrography. Hydrography is the most important layer to feature to generalize in Canada. 65% of our database are related to water or toponyms to water. So it's prime importance. If you want to achieve good generalization with hydrography, you have to stop thinking at the hydrography as a graphical layer, but really start thinking about it as a network. stop thinking about it as being by tile and start thinking by watershed. The first step was to generalize a hydro network is to derive a skeleton, set flow direction for each line using a DEM, and for the line that were not able to be oriented with the DEM, there's a new transformer that will help to solve the remaining of the problems. Second step, differentiate primary network lines from the secondary network line. We do this by knowing what is the sink of the network, identifying the different sources. Then we find the shortest path from the sink to the source. We do this for all the lines. We are at that moment able to know what is the primary network, solid line, from the secondary network line, dash line. We also are able to move from a network with cycle to a tree, which is a network without cycle. Two other transformers that were done, stream priority calculator and shortest path finder, help us solve that problem. Third step is to apply a stream ordering system. I don't know if there are geographers or geomorphologists in the room. You probably know, and better than me, what about Stroller ordering and Orton ordering is. In the first step, we apply Stroller ordering. So from the sources, all the leaves, we gave them a Stroller order of 1. When you've got a Stroller order 1 meets another 1, becomes a 2. When you've got a 2 and a 1, it remains a 2. And you do this recursively on all the 3. So for this example, we've got a Stroller order of 3. In the second pass, we apply Orton ordering. And this, we're doing the opposite. We start with the sink, and we try to identify, well, what could be the main channel from the source, from the sink to the sources. So you start with what you're saying, and you go uphill. At each bifurcation, you have a choice. Should I take the straightest path, the longest path, the named river, or any other kind of priority? And all those features are parameterized within the new FME transformer. So for this one, I choose probably the longest path, and I said, oh, this one is probably, the software said this one was the main channel, and then you do that for the channel -1 and -2, and you apply the ordering system for all the lines. And we do all this for that final step, which is the fun part. We apply line selection based on Orton ordering. And what's even more fun is that the results are very comparable to what a human cartographer would do when he's doing hydro network generalization. Also, it's objective, it's repeatable, and it's scaleless methodology. You can apply it at 10K, 50K, 250K. And the Orton stream ordering system will tell you that each time we remove one level, we remove about 1/3 of the elements. Small rivers are also a big problem, bottleneck. A cartographer don't like to have what they call sausage effect, where it becomes thin and you got a small line, then a lake, then a small line, then a lake. So we have to find a way to solve that problem. We use the FME triangulator to find all the bottleneck problems. Then by applying different kind of measure on those bottleneck areas, we were able to decide which generalization operator to apply, either enlargement or collapse in that case. Other new tools that are useful in FME 2010, oriented bounding box. If you want to find the width and length of a feature, well, I prefer that one than that one. Rescaling of an object to a target area size. You're mapping southern Alberta. There is one tiny lake in the whole file, but it falls just below the minimum size. Well, you probably want to keep it, but you probably want to increase the size to meet your minimum size criteria. Another classic operation in generalization, Nickerson displacement, where you would like to move part of a line. In this case, we are not moving all the feature, but just the part of the line that are too nearby another element. So in conclusion, the qualitative results of the prototype are very encouraging. We are in the phase of doing a quantitative evaluation. If we're still happy, next step, building a production generalization process. We'd like to work again with safe software to enhance FME with missing generalization algorithms. Investigate how we could automate the behavior level. If we go back to that slide, last time you're going to see that one. But it's to work on here to implement new operators and to see here how we could implement a behavior algorithms. Conclusion for you, for the community. Well, I think you've got new tools now in FME 2010 adapted for generalization measure, generalization operator. If you want to do generalization, well, shut down your workbench, unload it from your computer, work with your cartographer, wait before going on behind your benchmark, try to understand what they are doing, write down those generalization rules. We use it in pseudo-English, use whatever you want. And don't forget the 4 principles of good generalization: measure, constraint, behavior, and operator. Thank you.